Hello and welcome. This is the section in chapter 15 called the pendulum. And there's two important types of the pendulum that we're going to consider. These slides have the simple pendulum, and then I will add a little bit about the physical pendulum because they're both really important. They both have the same idea of them and the same approximation. So for a simple pendulum, we're modeling it as a small mass attached to a massless rigid rod. If it's a string or a rope, then the rope is flexible, and it's not a rigid body. The bottom of the string will kind of oscillate faster than the top, and so it'll be kind of wavy like that. So the rod has to be rigid, and furthermore, it has to be massless, at least for now. That's what a simple pendulum is. It's a massless rigid rod connected to what we call a point mass at the edge. And so the rod, we say, has a length L, lowercase l. And so what are the forces that act on this pendulum? It's kind of a confusing one if you look at the forces for all times, because you have to do this coordinate system from chapter 8 called the RTZ coordinate system. This figure certainly does have that. It has the t-axis, this lower right-hand figure, has the t-axis pointing in the direction of motion. The r-axis points towards the center of oscillation. And so it's acting under obviously the constant influence of gravity, but the very dynamic, very changing influence of the tension in the string or in the rod. This tension will change from point to point, obviously in direction, but also in magnitude. For instance, when it's swinging at the bottom, when the velocity is largest, the tension is extremely large, pointing towards the top. And as it gets further out in the angles, the tension, while still pointing towards that axis, gets smaller and smaller. So it has a weird shape as a function of angle. But the tension actually doesn't matter for the oscillation of it, because it's always going to be canceled or have some it'll interact with the component of gravity that points parallel or more precisely anti-parallel to it. So we have a radial component of mg that points against the tension. Now that actually isn't zero. Those, if you remember from chapter 8, those actually add up to mv squared over r, a net force that points towards the center. Again, that's not relevant to the oscillation. What is relevant to the oscillation is this little force, this little tangential component of gravity. Once again, that's always changing, and it depends on the angle. And so if you do the analysis on it, you find that the net force on the simple pendulum is equal to minus mg sine theta. And then so the acceleration is equal, the acceleration along this along this s coordinate, which kind of is the coordinate, the arc length coordinate, it's equal to minus g sine theta. So this isn't quite the formula for simple harmonic motion. We have on the left-hand side, we have the acceleration of the particle in the arc length coordinate. We have a g, but we have a sine theta here. And if the angle is big enough, then that's really all we can do. And we have to resort to solving this equation by a computer, because something like this isn't solvable, at least in a closed form analytically. You can certainly express it in terms of a power series, but that's beyond the intro analysis here. What is important for this analysis is this small angle approximation. So the small angle approximation assumes that the oscillation of this pendulum is small, less than 10 degrees or so. And when you assume that the oscillation is less than about 10 degrees, then sine of theta is approximately theta. The way to visualize this approximation, without going into a big discussion about Taylor's theorem, is to just quickly think about the sine graph. If you were to, for instance, graph it on a graphing calculator, it would look, if you graph sine of theta in the lower right-hand corner of the screen, the graph would look something like this. Let me grab my pen. Grab the wrong color. Okay, dark gray. So obviously sine of theta looks something like this, right? So if you graph theta, or if you have theta on the t or on the horizontal coordinate and sine of theta on the vertical, then obviously it's going to be something like this, right? And if you zoom in enough on the sine graph, then very close to the origin, it looks exactly like the function theta. It makes more sense, I think, when you talk about it as sine of x. But very close to the origin, that is for very small values of theta, sine of theta is approximately theta. And so since sine of theta is approximately theta, you can replace those. You can you can set sine theta equal to theta. And then, so that's this approximation that they make right here. But then they say that, well, theta, if it's on a radius, constant radius, that's equal to the arc length divided by the length. The picture that you want to keep in mind for that is, if this is the arc length s along that coordinate of interest, then it's proportional to theta, the length of the thing. So we have the typical equation for arc length, S equals L theta, and so you can replace the theta with S over L. Well, sure enough, that actually finally gives you the equation that you needed to show that the pendulum has a simple harmonic motion. And that result then is, you could express it in terms of the angle, which oftentimes is confusing, or you could express it in terms of the arc length. You get d squared s dt squared equals minus g over L times s. And so we have that equation that we needed. And so this g over L is the angular frequency of the simple pendulum. So we see that the simple pendulum doesn't depend on the mass. And more importantly, it actually doesn't depend on the amplitude either. So there's really interesting videos out there, or you can even look at it, two children swinging on a park or swinging on a swing at a park. They have different masses. They're accommodating for their slightly different centers of mass, then they'll more or less swing up and down at the same rate. That's the idea. And then also it depends on the L. And so when you think about this angular frequency means that there's a very, very small angular frequency for very long strings. Right? Small angular frequency means large period. And a small length, well, that's like a little dog's leg, like a little puppy. If you see a little puppy walking, their legs are oscillating back and forth very quickly. That's a large angular frequency. So that's the analysis of a simple pendulum. There's not a slide for this, but I wanted to quickly show how there's an analogy for what's called the physical pendulum. And in the physical pendulum, we have an object that is not a point mass. It's not a simple mass. It's a three or two-dimensional object. It's got a certain center of mass. Right? It's mass m, and the axis is usually given away from the center of mass, and so there's distance d right here. How is this a physical pendulum different from a simple pendulum? Gravity still exerts a force downward, but since it's a rigid body, the gravity exerts a torque around that axis of rotation. And so the expression for the torque is tau equals still, it'd be mg times d times sine of theta. So that is the gravitational torque that is exerted on the rigid body. It, again, torque in this case would point let's see, if you do your right-hand rule, the torque would point into the screen here, and then as it swings to the other side, it'll point out of the screen. But this is the equation. And if you remember from chapter 12, this equals moment of inertia times alpha, which is d squared theta dt squared. So we're actually very close to our equation of second derivative proportional to object. So once again, making that small angle approximation here for theta less than or equal to 10 degrees, we once again arrive at our equation relating the second derivative to minus the value of theta. Again, I guess we need to include the minus sign in the torque because it's always towards the center. And we get that the angular frequency for a physical pendulum is equal to the square root of mgd, mass of the pendulum, mass of the object, times free fall times d, the distance of the center of mass of the axis, divided by the moment of inertia. And so oftentimes, of course, the moment of inertia will also be a function of the mass. And so we get that the mass cancels in some way. Now, if the moment of inertia, now if the object has a variable density, then it'll be slightly different, but the mass, the kilograms should always cancel in that explanation. So that is another important example of using dynamics to calculate the angular frequency of an oscillating system. This is something that's very common in many areas of science and engineering as well, where you take some equations, and if you're able to get it into that form, then once again, you have that system is oscillatory. Certainly something that we do in waves in the next couple chapters, something that they do when we're studying properties of light, for instance, or AC currents for AC circuits. The electrons inside the metals are oscillating. Sound, other examples of oscillating behaviors. So this certainly is one of the most fundamental types of motion in the universe. And that none of this is including any dissipation, a topic we'll talk about in the next video. So thanks for your time, and we'll see you back here for damped oscillations. Take care.